Hi everyone, this video is the solution to example 3 on the topic of flexibility method. Similar to the previous example, we have again 4 reactions. So we have 2 reactions at A, the vertical and the horizontal, and we have 2 reactions at D, the vertical and the horizontal. In this example, we're going to choose to remove the reaction at A, the horizontal one. So what we're going to get is a structure with a roller support at A and then a pin at D. And then our structure number 1 has all the loads. In this case, it's just the load of 72. And this is going to be plus another structure, also with a roller on the left and a pin on the right. But now we're going to apply 1 kilonewton to the support that we removed, which in this case was HA. And at the end, to make sure we have an equivalent structure, this needs to be multiplied by HA, which is what we're going to use to calculate this reaction. Similar to the other examples, what we're interested in doing is finding out the horizontal displacement at A in structure number 1 and as well in structure number 2. So off we go. To calculate this, the first thing we need to do is the bending moment diagram on structure 1 and also bending moment diagram on structure 2. If we look at structure 1 and we start with the reactions, we know that the only way we can resist the 72 is with that reaction at HD. And the 72 is here. This also creates a torque in the clockwise direction, right? Like this. So we need to balance this out with counterclockwise reactions. So our vertical reactions need to do the opposite motion. So something that looks like that. So that means this is down and this is up. The total amount of torque we have is 72 times 4 meters. So again, the distance between the two loads. So 72 times 4 is equal to 288. And our reactions have a distance of 6 meters. So I'm going to divide the 288 by 6 and conclude that these reactions have to be 48 and 48. I used a bit of space in calculating the reactions, so I'll draw the bending moment diagrams underneath. But let's just calculate the reactions on structure 2 before we do that. So we know we have 1 kilonewton acting on A, and that means our reaction at D also has to be 1 kilonewton. And now, if you pay attention to this, the torque that these two forces do is actually 0 because they are aligned with each other. So there's no perpendicular distance between these two loads, which means these reactions here are also going to be 0 because your moments are balanced, your horizontal forces are balanced, so then your vertical forces both have to be 0, otherwise they will cause problems with equilibrium. But okay, now that we have the reactions, let's now do the bending moment diagrams. If we look at the column on the left, the column AB, we can see that it doesn't have moments because there's no shear force and there's no concentrated moments. That means the moment at B is 0. And now we have the 48 pushing point B down. So when it pushes down, we should have tension on the top side. So we should start having our diagram being drawn like this. And on that side, it's going to be 48 times 6, which is equal to 288. This gets transferred outside. So that's going to be my moment over there. And then it needs to close at 0. Just to confirm, we can look that the load of 72 also bends our column like this. So then it has tension on the right side. And then 72 times 4 is also 288. So this moment should be correct. For our other structure, we can see the load on the column on the left. So this load of 1 kilonewton is going to bend our column like this. So tension on the left. But the other load on the other side is going to bend like this, so tension on the right. So we can start drawing that this is going to look like this, and this is going to look like that. So tension on the left for the left column, and tension on the right for the right column. The total value of the moment is 1 times 4, 4 being the height of the columns, so that means this value here is 4, this value here is 4. If we transfer this outside, those two values also have to be 4, and now we're kind of thinking, how can we connect these two dots? If we look at the vertical reactions, so if we look at these vertical reactions, they're 0. So that means the shear force in the beam, so in the bar BC, the shear force is 0. What that means, that doesn't mean the moment needs to be 0. What means is the slope of the moment is 0. So we can connect these two dots with a straight line and realize that this slope here is 0 because the shear force is 0. So okay, now we have our two diagrams. We're in a position to calculate our displacements and then conclude the problem. So the first thing we're going to do is the horizontal displacement at A from structure 1. And in this case is the column on the left, so that's 0 times the triangle divided by EI, that's just 0, plus the beam, so that's a triangle, times the square divided by the EI of the beam, plus, and now finally we have a triangle times a triangle divided by the EI of the column on the right. Since all the EIs are the same, we can add them up at the end. So here we get 0 on the first one, and then triangle times square is 1/2 ACL, and then triangle times triangle is 1/3 ACL. And pay attention here because we need to make sure this applies to the triangle and the square. So 1/2 and then ACL. So if we look at the triangle, should be 288. The square is 4, and then the length of the beam, in this case, is 6 meters, plus, and now we're going to do the column. So 1/3, and now ACL. So the value on the triangle on the left is 288. The other triangle is 4, and then the length is also 4. If we add this up, we have 3,456 plus 1,536. So this gives me 4,992 divided by EI. In this case, the diagrams are all on the same side, which means this is indeed positive, which means this displacement is in the direction that I'm assuming from the beginning. So this displacement is to the right side. Now, similar to before, let's look at the structure and think if it makes sense that this point is moving to the right. So if we're pushing the beam on the top to the right, it makes sense that the beam is going to be pushed to the right, so probably this point is also going to be pushed to the right. So that makes sense to me, that the displacement is to the right. Okay, so now we're in the position to do the horizontal displacement at A for structure 2. And in this case, it's just the diagram number 2 times itself. So it's a triangle times a triangle, square times a square, plus a triangle times a triangle. So triangle times triangle, plus square times square, plus triangle times triangle. All of this divided by EI. If you look at the table, the triangles, we know it's 1/3 ACL. The 2 squares is just ACL, and then the other triangle as well, 1/3. So now if we look at the diagram, when we do the columns, the length is 4. When we do the beam, the length is 6. And then all the values of A and C are 4. So we can write this down as 1/3 times 4 times 4 times 4. And I'm going to times it by 2 to account for this one here. And now plus 4 times 4, and now times 6 because the length of the beam is 6. In this case, we have 64 divided by 3 times 2 plus 96. So we get 416 divided by 3 EI. And in this case, it's always positive, which in this case also means it moves to the right, which again, stop and think a little bit here. If we're pushing that point to the right, it makes sense that it will move to the right as well. So this is the displacement we just calculated. Okay, so now let's get our compatibility equation. We know that the actual displacement at the support A needs to be 0. And we also know that that is nothing more than the 1 from structure 1 plus HA times the 1 from structure 2. If we replace the values now, 4992 EI plus HA, and now 416/3 EI, we now can see that HA is actually going to be negative, and it's going to be 4992 divided by 416 divided by 3, so we get minus 36 kilonewton. And the meaning of this minus just means that whatever we assumed in the beginning, and we're assuming always to the right, that means the reaction goes to the left, which again makes sense because without the support, the structure wanted to move to the right. So what the support is going to do is push this displacement back to 0, and that force therefore needs to be to the left. Now if you look at the structure from the beginning, which can be a good exercise, it makes sense that that 72 is pushing the structure to the right. The only way the reactions can prevent the structure from moving at A and D is if we push it back to the left. So at the end, always spend a little bit of time to understand if your directions and your positive or negative signs make sense. So minus 36 is good. So now finally, we want to do the final bending moment diagram. And we know that this is nothing more than taking the 2 diagrams we have and multiply the second one by minus 36. So let's draw them down again before we finish. So the first one looks like this, with these maximums being 288. And now we know this is plus minus 36 times, and now the other diagram that has the 2 triangles and the square. And we know all these values here are 4 and 4. So, okay, what does the minus 36 basically do to the diagram from structure 2? Not only scales it by 36, but also flips it around. So we have to be a little bit careful with this. Let's see if we can solve this straight away in this final diagram. So in the column of the left, if we look at the column of the left on structure 1, the moment is 0, and then the other moment is a triangle that is on the outside. But because this is minus 36, right, that minus sign there is saying the moment is not outside, but it should be inside. So that's going to be my moment over here, and that value is going to be 0 plus 4 times 36. So that is 144. So if we have moments inside, they get transferred inside. So the moment on the beam will also be 144. And if we want to know the moment on the other corner, we have 288 from structure 1, and then we have 4 times minus 36 from structure 2. So actually, these two moments are on the same side, but because there's a minus, again, on the 36, the 4 needs to be flipped to the other side. So what we're going to get here is 288 minus 36 times 4. And we also get 144, which means this moment here is going to be 144 as well. So here we can connect these two with a straight line. And just so you don't forget, this 144 is nothing more than 288 minus 36 times 4. Now we know this gets transferred outside, so here they go to the column 144. And this makes sense because we're using the same numbers as before. And now we know this closes at 0. And this is it. This is how the final diagram should look. I hope this made some sense. Flexibility method is not a complicated topic to understand in principle, but it takes a lot of work. You need to be very good at the diagrams, so practice as much as you can, and you'll see that it's going to get better. So thank you for watching this video, and have a nice day.